Now it's time that we are going to learn what is the equilibria constant and how do we calculate it. So the equilibria constant is given the symbol of K because it's a constant here in chemistry. And just like the rate constant from the previous chapter, this constant is specific to the equation that we're talking about. And when we have this K, though, notice now that it's going to be an uppercase K value. In order for us to calculate the equilibria constant, what we're going to need are the values for the pressure of each gas, and they must be each gas at equilibrium. We can also do this if we have aqueous solutions. We need the concentration of each species at equilibrium. All right, and so we can calculate this equilibrium constant that we're going to call K. All right, now it also has this thing in here that's called an equilibrium quotient, Q. We'll see this a little later. All right, we're going to save that for a little bit later. Right now we're focusing on the equilibria constant K. All right, next it says the value of the equilibria constant is independent of the starting concentration or pressure of the reactants and products. All right, so what that's saying is that it really doesn't matter. If we were to go back to our example of our N2O4 decomposing to two NO2s. All right, what it says then is, what this means is, like, if you had a container that only had some dinitrogen tetroxide in it, and you let that go to equilibria, you're going to reach a value for K. All right, now if you had another container that only had nitrogen dioxide in it, and you allowed it to sit there and go to equilibria, you would reach the exact same value for your equilibria constant. K would be the same. It doesn't matter if you start with only one or only the other. Heck, you could start with a 50-50 mixture of them and you'll still reach the exact same K value. So it doesn't matter what you're starting with, you're always going to arrive at the same equilibria constant. All right, the equilibrium constant is dependent upon temperature. We will calculate the equilibria constant most of the time at a specific temperature, and then we could talk about what happens when we change the temperature. We're going to do that a little bit later on. All right, but the equilibria constant does change when we change temperatures. Let's take a look at solving for the equilibria constant here. And so what we see is that if we have a reaction where we've got all of our species, in this case our gases, and we've got our generic equation up there again, like I said, we're not going to get away from that guy anytime. And we've got our species and we've got all of our coefficients. In order to solve this, and to solve this for anything, and get this thing down, because it's not an equation that you're going to be given. This is an equation that you're going to use so many times that you're going to have it down pat. Notice that I have, for my equilibria constant K, we have the partial pressure of C raised to its coefficient times the partial pressure of D raised to its coefficient. All right, so notice that this is products divided by our reactants. And we have to make sure that we raise each thing to the corresponding power that goes with it. In order to use this equation, we are going to always express our pressures in atmospheres. All right, now, depending on your books and stuff like that, some of them are okay with you doing things in millimeters of mercury and stuff like that. Those are wrong, all right, because we have to use atmospheres, because we can normalize atmospheres. All right, and when we normalize the atmospheres, then we're going to find that our K has no units. All right, it's going to seem like K is going to have units. When you start working problems, you're going to have ones where you're going to have like atmosphere squared on top divided by atmospheres, and you're going to want to be like, that's got to be atmosphere squared divided by atmospheres. It's got to be atmospheres. It's not. Technically, you are not using atmospheres. All right, you are using a normalized version of atmospheres. Is why we have to use atmospheres in there is because we normalize them, and we do that behind the scenes. You don't have to do anything to do that. If you plug in atmospheres, you're going to get the right answer. Make sure that your K has no units. Reason I know it has no units is because later on we're going to be taking the natural log of K, and you can't take the natural log of anything that has units, so it can't have units. All right, but this is our generic way of writing this, so get used to seeing this. We are going to use it a whole bunch of times throughout this entire semester. All right, now we can do the same thing for if all of our species here were concentrations, right, where they were aqueous. And notice that the equation itself is ridiculously similar to what we just had for pressures. All right, notice that I'm going to give this the symbol of Kc, meaning that this is for the concentration equilibria constant, just meaning that everything in this has a concentration associated with it. And in this case, all of our concentrations are molarities. All right, so make sure that all your concentrations are molarities, but it's still the same thing. Products divided by reactants raised to some power, right? Raised to the power of each one of their coefficients. All right, now, if we were to relate our Kp, that it was everything was in the pressures, right? If all of them were pressures, and we were relating that to everything being concentrations, we could use this equation down here on the bottom, where our Kp is equal to Kc times our R, that's our old school gas constant, times our temperature in Kelvin, raised to the change in our number of moles of gas. Okay, we will never use this. All right, this is an equation that, you know what, might sneak into homework somewhere, and that's the reason I put it in there. I tried to wipe out all of those possible questions, but every once in a while one gets through, one sneaks through, especially when they change questions, and I can't go back through and see what they've added in. It's the whole rigmarole of what the homework, online homework does. So I will never ask a question using that on an exam, right? We will, yes, use this. All right, that one's important. Well, what if we wanted to change our chemical equation? All right, so if we wanted to change our chemical equation, and this is one of those topics that for some reason students do not focus enough attention on. This is another topic that is going to be used quite a bit. So get this down. All right, get this now. All right, if we were to change our chemical reaction itself, all right, we're going to change the K. So remember that K is specific to the reaction as written. Okay, let's say that we took a reaction and multiplied through all of the coefficients. By some number. Our K is going to be raised to that power. All right, so in this case I have, right, my N2O4 and my NO2. All right, so remember originally, and I'm going to run out of places to put stuff on this slide. This could be like over 3 slides for the amount of stuff that we need on here. All right, but original equation was N2O4 in equilibrium with 2 NO2s. Right, that was our original way of writing our equation there. All right, notice that, right, I have taken that original equation and I've multiplied my coefficients through by 2, so now I have 2 N2O4s and 4 nitrogen dioxides. All right, so it says that we are going to then raise our K to that power. So our original K was the partial pressure of NO2 squared, right? That's our product raised to its power, divided by the partial pressure of N2O4. All right, well, the K for this reaction up here is the partial pressure of NO2 is now raised to the fourth power divided by the partial pressure of NO2 raised to the second power. So the second one there, that one is really the original K raised to the power of 2. And we can see that mathematically, right? Let's say that the partial pressure originally, right? So let's say that the partial pressure for NO2 is 4. So let's say that that was 4 squared divided by, all right, say the partial pressure for N2O4 at equilibrium was 2. All right, well, 4 squared divided by 2 is 8. All right, well, let's do that for when we had our N equals 2. All right, well, then we have 4, but now that's raised to the fourth power divided by 2, and that is now squared. Well, 4 to the fourth power divided by 2 squared is 64. Well, 64 is also 8 squared is 64. Right? And so if we took our original K here and I squared it, we get this value. So when you multiply through any equation by some coefficient, you can take the original value for equilibria constant and raise it to that power. Right? In this case, right, if I multiplied through now by 1/2, I would take the original K and raise it to the 1/2 power. Right? And then the bottom says reverse reactions are reciprocals of these equations. So, all right, let's say that I took my original equation and I reversed it. So we have 2 NO2 gases in equilibria with N2O4 gas, right? I just took the original and I reversed it. Well, K for this is now the partial pressure for N2O4 divided by the partial pressure of NO2 squared. Notice that the things here that I'm going to box out in my green are reciprocals of each other. And so the K for the bottom one is the original K, but it's 1 over K original. All right. If it didn't click home with you on doing that, right, make sure that you get some extra practice working those. Manipulating equations is going to be big as we go through these. And when you manipulate equations, you're going to have to manipulate your equilibria constants as well. Next, we're going to talk about coupling reactions together. And remember, from Chem 1, that means when we're going to add chemical reactions together to get an overall reaction. Right, if you look at my example here, if I took these top 2 reactions and I add them together, remember that we're going to take anything that we find as a reactant and a product. So here we have a reactant of a half an oxygen, and it's a product there in the second one. They're going to cancel out. And that's leaving us with our sulfur dioxide plus nitrogen dioxide and equilibrium of sulfur trioxide and nitrogen monoxide. All right, now, when we did this for delta H, coupling reactions meant we added, right, which is also calling or took the sum. We added up the delta H's. Right? For our equilibria constants, we are taking the product, which is a fancy word for multiply the K values. So for this one, right, this is 2.2 times 4 will give us our overall K. When we add reactions together, we have to multiply or take the products of our Ks. Again, it's a topic that for some reason students don't focus enough time on. I guarantee There will be questions on at least 2 exams throughout the semester, and probably the final exam as well, which will put it on 3 exams that will deal with the previous slide and this slide. All right, let's say that we are going to look at this equation up here where we know that the K is 0.76 for the reaction of sulfur dioxide, 2 of them, and an oxygen to be at equilibrium with 2 sulfur trioxides. It wants us to calculate K for the synthesis. All right, so the synthesis of 1 mole of sulfur trioxide. So this is a fancy way of saying that that's going to be a product. All right, so what we want to do is we want to write out the equation first. So we are making 1 mole of sulfur trioxide here as our product, and it's going to be at equilibrium. Well, if we only have 1 mole of that, then we have to then divide the coefficients of the reactants by 2 as well. So we're going to have sulfur dioxide and 1/2 of an oxygen in there. All right, so what we have done is we have taken our original equation and we multiplied through by 1/2. And so we are going to take the K and we are going to raise it to the 1/2 power, right? We're not going to multiply K by 1/2. We're going to raise it to the 1/2 power, right? Which is the same thing as taking the square root of it. And so our new overall K for this is going to be 0.87, right? So make sure you know those rules on working with these things. All right, another one here with that same problem, but in this case, we are going to decompose 2 moles of sulfur trioxide. All right, so that means that we're decomposing the sulfur trioxide. That now means that this must be a reactant. All right, so we've got our sulfur trioxide as a reactant, and we're decomposing 2 moles of it, so I'm going to put the 2 out there. All right, so I've got my 2 moles of sulfur trioxide, so now then the products are going to be what used to be reactants, and I didn't change the number of the coefficients, so it's still going to be now 2 sulfur dioxides and 1 oxygen in there. All right, so all this equation is the reverse of our original equation. And so in order for us to get the new K, so K for the new reaction is 1 over K original. All right, so 1 divided by our 0.76, which will give us 1.3. And I remember, again, these do not have any units, right? It's just 1.3. The last slide here in podcast 2 is about heterogeneous equilibria. All right, if we have any liquids, right, pure liquids or solids, right, they are not going to affect our equilibria. They are just going to sit there, right? And so because they do not affect our equilibria, they will not show up in our equilibria expression, meaning that they are not in our equilibria expression for our K values. All right, now what we do is we need a placeholder of 1 for mathematics purposes. All right, and so as long as there's even a little bit of a solid or a liquid or a gas, or sorry, a solid or a liquid in there, right, we're going to leave it out of the expression for our equilibria constant. All right, but if it is only in the numerator or only in the denominator, right, if it's alone by itself, we have to put a 1 in. Right? It's not like it's 0. We're going to put a 1 in. And so we'll see that as an example a little bit later on in this chapter as we're working problems. But notice down here on the bottom, right, I've got my expression for K here. K is the partial pressure of my carbon monoxide. All right, notice that the water is left out it's really just 1 for the water. And then we're going to divide that by the partial pressure of our carbon dioxide times the partial pressure of the hydrogen, right? So we've got still our products divided by reactants. We just left the water out of our equation there. All right, that ends podcast number 2 for this chapter. Next, we're not only going to take the equilibrium constant, but we're going to start to see how we calculate it.